group. Today I'm going to talk about HPCC, high precision congestion control. HPCC controls the congestion precisely, so it can maintain near zero queue for ultra low latency while maintaining very high throughput. Today, high-speed networking is desired in the cloud because new applications such as high-performance storage, large-scale high-performance distributed deep learning use new hardware which can generate and process data order of magnitude faster than before. They also require ultra-low latency, so network is becoming more important. Second, resource disaggregation is happening in the cloud, which separates compute, storage, and memory into different pools. So even memory access will likely go through the network. And they also require ultra-low latency, so the network becomes new bottleneck. So there are two essential steps towards high-performance networking. Because CPU cannot keep up with the high speed, so offloading network stack into hardware is inevitable. And we recently have tons of effort on that, such as RDMA and SmartNICs. However, with offloading, the sender can generate data much faster, which causes even more severe congestion. So we need to solve the congestion control problem as well. From running RDMA networks for many years, we found that today's congestion control faces three essential challenges. First, if the congestion control cannot control the queue length, then we trigger the queue offload and the PFC storm, even deadlocks. However, we cannot disable PFC because it causes bad performance. The second, we cannot run both high throughput and low latency applications in a single cluster because today's RDMA, you can if you run very high throughput, you can easily increase the latency as well. So one solution is we separate those applications into different network queues, but we don't have so many queues for different applications. Last, today's congestion control algorithm requires so many parameters. For example, in RDMA, the DCQCN requires at least 15 parameters. So with so many parameters, it's really hard for us to tune those parameters before going to production. To sum up, today's congestion control causes slow convergence time, and also long queuing delay, and also the complex parameter tunings results from the heuristics using in congestion control. To solve those problems, we propose HPCC. The key idea behind HPCC is that we use precise link utilization information from the network telemetry to control the rate update precisely. So here is how it works. For each packet sending into the network, goes through each hop of the switch. So the switch adds INT information into the packet. And once the packet arrives in the receiver side, so the receiver sends it back to the sender with the INT information. So according to the INT information, the sender adjusts the flow rate accordingly. So HPCC solves three problems by using INT as a process feedback. First, they can achieve very fast convergence because the sender knows precisely the rate to adjust to based on every single ACK. Second, we can achieve near zero queue because the feedback does not rely on the queue. The last, HPCC has few parameters because we have process feedback, so we don't need those heuristics to adjust the sending rate. To evaluate the performance, we build a small-scale cluster with 8 servers. Each server has 2 NICs with 25 gig. And this cluster has 3 layers of network switches. And also, we use the RPC trace from the production storage system to evaluate the congestion control performance. To test the congestion control performance under a very high load, we evaluate the traffic load upon 80%. And also, we use a very light-tailed traffic trace. From this CDF, we can see that, for example, 90% of the query are less than 32 kilobytes. So here shows the experimental results. First, we want to show the query completion time slowdown, which is the query completion time normalized by when there's only one flow in the cluster. And also, we only show 99th percentile in this figure. So we deploy HPCC in both RDMA and the TCP networks. In RDMA, we compare HPCC with the DCQCN, which is the default RDMA congestion control algorithm in modern RDMA NICs. And we can see that HPCC reduces query completion time quite a lot if we see the orange curve versus blue curves here. And in the TCP, we compare HPCC with the New Reno, and we can see that the green curve with HPCC reduced the query completion time quite a lot compared with the red curve. Specifically, we can see that given the 4 kilobytes query, we achieve 96% reduction in TCP and 81% reduction in RDMA. To show why HPCC can achieve this query completion time reduction, we also draw the occurrence distribution in the network. And here we can see that with HPCC, we can achieve near 0 Q even in the median of the distribution. And if you look at the tail, in the 99th percentile, with the TCP, we can achieve only 65 kilobytes queuing delay buffer, and which translate to around 20 microsecond queuing delay. And RDMA, similarly, we have 17.4 kilobytes in the tail. That's all for the presentation. Thank you.
Muted.
Should I ask a question here or just type in the chat window? Hello, can you hear me? Oh yeah, so for the in-class program, so HPCC, basically with HPCC, we allow RDMA to send the traffic in line rates at the beginning. So with that being said, in the first round trip time, you will send traffic at the full line rate. So we will use buffer to handle this traffic. And then after the second round trip time, HPCC will work and adjust the rate based on the feedback. So the issue was the first round trip time for the in-class traffic. What we do is we control the long flow so that it's very close to full line rate, but just a little bit slower. For example, we can use only 95% bandwidth or 98% bandwidth, so that we can achieve near zero queue in the network, so that we can have a bunch of buffer to handle the traffic in the first round trip time. And beyond that, because we only use 95% of the bandwidth, then we have 5% headrooms. Then we use the headroom also to handle the traffic in the first round trip time for the in-class scenario. And we have evaluations to evaluate that. We can handle very large in-class degree. Oh, I see. So because the ECM mark is just a single bit indication of a congestion, with INT, we want to quantify the in-flight bytes. So in-flight bytes mean that how many packets that you send into the network without being acknowledgement yet. So we want to, so the way we quantify the in-flight bytes, we use the TX bytes and the Q length together to quantify the in-flight bytes. The TX bytes mean that how many bytes the switch port sends during this time period, and also the Q length means that how many bytes the switch still need to send. So together, these two quantify the utilization of a particular link, so that we use that to quantify the congestion degree. For the PFC, it's kind of a flow control mechanism, and we think it's orthogonal to the congestion control. So you can either use PFC or not use PFC. So the way the congestion control or HPCC works is to control the Q length. If there's any congestion and Q build up, you see Q length. High performance control like HPCC, you can actually reduce the Q length to, like in HPCC, we can reduce the Q length to near zero Q. Then you don't have to use PFC at all. We have evaluation in the paper show that we don't actually turn on PFC for the entire evaluation. That's a great question for the HPCC work without anti-capable network switches. Yes, because usually we run a large-scale network. We have only a part of our switch to turn on anti-capability. Then in those switches without anti-capability, we use other mechanisms like ECN or RTT timestamp to control the congestion within those switches. So we have a large-scale hyper mechanism to control congestion in the production. If the multiple nodes send the feedback, so the anti-frame actually just quantify the congestion degree for a particular node or particular link, right? So what the congestion control is that they want to minimize congestion the bottleneck link. So firstly, you want to compare the bottleneck link, then use that bottleneck link anti to control the link speed. However, if the bottleneck link changes from the one link to another link, we need to switch the context. Yeah. Yeah, we we actually deployed our HPCC and Alibaba, so we run very large-scale networks, and also we deploy in TCP protocol as well. So we run very large scale. We see a lot of issues. Yeah. So for example, in TCP, you don't have very precise traffic control. Like you actually send the traffic in a burst. Like you have a TSO enabled, then of course cause some problem for the congestion control. Then you need to have a very conservative setup for the buffer in this case. Oh really? Hello. How about now? Yeah, we run very large scale in our production. The way we use INT, like that's quite different with the production deployment. For example, we need to generate the problem package to query the INT information for every round trip time instead of every packet. That's based on some limitation on the device. And also the challenge in that we have to work with TCP traffic. So we have a separate network queue for TCP and HPC traffic, and we need to consider the QoS between TCP and HPC traffic. Those are also challenging as well. That's a great question. We actually thinking of that, but we generate INT information because most of the congestion happen in the last hop. So it really doesn't matter if we send backward or forward. And if you send forward, just get it to the destination and then send it back, because it's all in the hardware data plans. So the difference is very small in my opinion. Sorry, I'm over time. So thank you. Please feel free to send me an email if you have any more questions. Thank you. Thank you, guys.